Okay, so welcome everyone. This is a video I've been looking forward to making for a really long time because we're going to look at some of the most sophisticated mathematics there is. We're going to look at it in a way where you don't need any prior experience to understand it. We're going to look at a tool which allows you to visualize all sorts of amazing things. It's this piece of software called Homotopy IO, which basically lets you do higher dimensional or sort of geometric higher category theory. And it's a really amazing thing. And so basically, I want to sort of talk about higher dimensional categories. I want to talk about how we can think about all these structures. And I want to show you how easy it is to do this stuff. And we're also going to have a look at another really important sort of tool, which is something called the periodic table of n categories. And this is kind of like a map or something, which is going to let us navigate this world of high dimensional structures. Now, I want to do something a bit different today, which is like a sort of different format where I'm going to be showing my friend Jos Hoebe about this stuff. So, hello, Jos.
Hello, Richard. Good morning.
Yeah. So Jos has been my friend for many years, and we've had many adventures in geometry and mathematics and many conversations over the years. And I consider him a very good geometer, and I like to tell him about these higher category theory things at different points. And um, so, are you ready for some
Of
Homotopy
course,
IO,
I,
Jos?
I love to hear it. Yeah.
Excellent, excellent. This is
I,
one
I, I,
thing.
I start with enjoying.
Yeah, this is one thing I always love about Jos. He's so he has so much curiosity for all of these things. So hopefully it's gonna enrich this experience looking at this with you, Jos. Um, so basically, we need to know about two things to get into this. One is what is a high dimensional category, and the other is how does Homotopy IO work? So let me start with this idea of categories and higher dimensional categories. So I know both you, Jos, and also some of the viewers on my channel, you'll already know what categories are, but let's start from the beginning anyway, because it, it makes it more complete. So everything's going to be super rough in this video. So let's start. So a category is where we have a load of objects like A, B, and C, and then we're going to have arrows that go between those objects, like this maybe. And then the key idea is that when we have arrows that head to tail, like these things, we can compose them. So we're going to have another arrow there. So it could be called G after F. And then the idea is that whenever we
Uh,
compose,
it
whenever
should
we
be it should be F after G.
no, it's G after F because we do G after we do F.
Yeah.
So there is alternative notation sometimes people use. So normally
Yeah.
we do
Okay. But
G after F, people write it like this, and then this circle here means after.
mhm.
But another notation that people is becoming more popular these days is this, um, which you could read as F and then G. So so you could read this as like then. Um, and
Oh,
this,
that's also interesting.
yeah.
Okay, thank you. That's a very nice notation.
So some people more in the modern times, particularly people like Spivak and things in the applied category theory, they use this, and it's better in a lot of cases, to be honest. It's the same order that we write things in.
Yeah, I like it. That I like better. Yeah.
I think, to be quite honest, it is better. But so much of category theory is soaked in this notation. I'm like somebody who learned to drive in a manual car who refuses to change to automatic. I'm so used to this notation, even though I realize that this might be better. I'm too ingrained in my habits.
Okay.
But yeah, so so I'm not really giving you a full definition of a category here, but I'm giving you the broad strokes. The really important idea is that we might have many arrows that go from A to C. And it's important when we're sort of defining the category that we say, well, we can compose this arrow with this arrow, and we need to say which one of these arrows that go from A to C is considered to be the composition of the other two. So that's something important. Okay. So,
and do you mean with it that A can have also the function, for example, D or X to C?
yes,
Okay.
exactly right. So we might have something called D here and something called X here.
Okay.
Maybe this one is H. So we say there's three possibilities that go from A to C. There's H, D, and X. And we say actually H is the one that is formed by composing F and then G. So this is sort of like you have a lot of numbers, and when you add two numbers together, you have to say which of the numbers equals the result, right? So okay, that's a category, like a rough idea. And then today we're going to be talking about higher categories, high dimensional categories. So we can start with two-dimensional categories. So how do we draw a two-dimensional category? Well, we start off like before. We have objects, and then we'll have some arrows. So we can start off just by drawing an ordinary category. Now, the idea is that when we have parallel arrows, like this one and this one, we might have what we could call a two-cell, which goes between the parallel arrows. So think of it as like a higher dimensional arrow, an arrow between arrows. So let's introduce a bit of notation. Maybe these are A, B, C, F, G, H, and alpha. So alpha is an arrow from, or a two-cell from F to G.
Carry on.
Okay, yeah. So the important thing, just like with an ordinary category, we should be able to compose the arrows. The important thing here is that we can compose these two cells here. So you see that these two cells are head to tail like this. So this that we could call beta after alpha, which is like the composition of these. So this is the basic idea, and then we can go higher dimensional as well. So these dots or objects, sometimes we'll call those zero cells because they're like zero dimensional things. And then
I have a question in between. Is that okay? You draw the composition of the two cells. Can there be a function also from that beta after alpha, as you called it, to C, directly to C?
Not directly to C. So the idea is that we keep everything what you could call globular. So the idea would be that we basically we're allowed to have objects, and then between zero cells we can have one cells. So like this, for example. And then for these two cells, those have to go between parallel one cells. So we have to go between one cells that have the same boundaries, if you like.
Yeah,
Like,
they go all to A and B. They are between A and B.
Exactly.
If you say it in lines, you would say more or less that A and B should be lines too, because that when you call it parallels.
Exactly. We shall see this very shortly. That's correct.
Okay.
Now, we can have higher dimensional cells, let's say, if we imagine we're working in a 3 category. So maybe we have these two cells. So let's recall the naming convention. These are 0 cells because they're 0-dimensional. The arrows we can call 1 cells because they're like 1-dimensional.
Yeah.
These are 2 cells. You could visualize them as surfaces or something. And then we have, or we can have, 3 cells like gamma that go between parallel 2 cells. And we can go on and on and on. So this is the idea very roughly of high dimensional categories. Yeah. So what we're going to do, Jos, and I think this is going to be fun.
One question. Is this kind of detailing, like you have a microscope? That's the way to see it. When you go into, because you can go after gamma into all kinds of higher dimensions.
Right.
Is that a more refinement, more like we see all these things with microscopes?
Yeah, definitely. That's definitely one way we can think about it. In some, there's one of the things you often do in category theory is you take some basic ideas, like say arrows that you can compose, and then you sort of see how much stuff you can talk about using those ideas. And we play a similar game with the higher categories. One thing we can try and talk about with them is, what does it mean to be equal? Or what does it mean for two things to be the same? And so we could say that maybe we have a thing called G and a thing called H. And we could say that maybe beta indicates in some sense that G is like H, or it's a way of converting from G to H. But maybe there's another way of converting from G to H, which is beta dash. And then gamma, that's like a way of saying that those two ways of converting are themselves similar. So it's kind of like introspectively zooming in on this notion of what it means to be similar in some sense, or
that's also a cool idea.
Yeah. So it's kind of like if you sort of start learning about like the foundations of maths, you can start saying, well, okay, someone tells you something and you say, well, prove it. Prove that G is like H. And so you go, okay, here's a 2-cell beta. And then I say, okay, but prove it a different way. And so you go, okay, here's a 2-cell beta dash. And then I say, but how do I know that those two proofs are the same? And you go, okay, well, I give you gamma, which relates beta to, and then I go, how do you know that gamma is, and you can go on and on and on. So this is kind of like this idea behind homotopy type theory, because it's the same idea really as like in geometry. You could say I have some space, and then I have, or it's a similar idea, I have points A and B, and then maybe I have like a path G and another path H. and then maybe I can continuously deform this path H to become like G. And maybe there's many ways of doing it, and then you can deform.
All paths lead to Rome.
Exactly, and to these ideas. So I think we're not being rigorous at all, but I think that's okay. Let's start the fun. So basically, there's only one other idea that we need to understand to get everything really, and it's the idea that this picture here and this picture here are showing the same information. So basically, this is like how category theory people often like to think about these situations. This is a sort of picture of a category as a directed graph. Whereas this kind of picture, which we think of as sort of being directed to the right, is what you could call a manifold diagram. And it's basically the same information as this sort of cellular diagram on the left, but it's kind of dual in some sense. So the really important thing to understand is how do we convert between these two pictures? And the key idea is that we replace the zero-dimensional things like this with one-dimensional things, and the one-dimensional things become zero-dimensional. So like over here, we have this, we have this arrow length, which goes from this object called word to this object called number. And over here, we say that length becomes a point, which goes from this line called word to this line called number. So this is the key idea. Yeah.
Does this have some kind of reason, idea, some why to do it that way? Why not the same?
Good question. So this,
because I myself would start, of course, with 0. So I could start with the same drawing, but then with a point segment and then point again. So
yes, absolutely. So these two pictures are showing similar information in a way, but the formal way to say what we're talking about here is it's this idea of what's called Poincare duality. So Poincare was one of the guys that kicked off topology quite a long time ago now. And he came up with this idea that you can dualize things. You can swap around the roles of, in this case, points and lines, and you get equivalent information. It's important for us, like pragmatically, because Homotopy IO works with these kind of things, what we could call manifold diagrams.
Okay.
And we're gonna like build up to this, but let me just quickly show you a sort of preview. These pictures on the right, these are manifold diagrams. And you see that when we start going high dimensional, the manifold diagrams, you can sort of think of them as made out of sheets and blocks and things that you can kind of bend and move around. And they tend to have more of a sort of topological flavor to them. So these ideas of being able to pull around strings or maybe twist things around or bend things tend to sort of make sense in terms of these manifold diagrams, whereas the cellular diagrams are more like kind of where you've got like loads of globules stuck together and they're like these cellular constructions. So these things are sort of equivalent, but they're like two different ways that you can look at something.
Okay. Yeah.
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 But yeah, I know you're very interested in this progression of how things move up when you start with zero and you can build things, and hopefully, like the way that Homotopy IO does things will you will like it.
Mhm.
So let's.
At least it looks very nice, colorful.
Yeah, well, that's it. At least it's colourful at the end of the day. If it, yes, so let's
Now,
begin.
what I also like is that it is a better kind of direct view, because at the left side, the old way to describe it with the dots and the arrows, it makes it such a mess always, more or less.
It can do, yeah,
Yeah.
yeah.
And I think this can order it better.
Yes, yes. I think you're right. I think a lot of this applied category theory seems to favor the kind of manifold diagram or string diagram approach, and I think there is maybe something about the way people think that relates better to the manifold diagrams. We'll see as we go on. You can tell me
Okay.
which you
Yeah.
prefer as we. So let's start with this, which is an example I usually like to give, the sort of first example of a category. So, like one kind of person that uses categories quite a lot are functional programmers. So maybe you want to write a program. So you could
You have
start
to
off
do the last part. You have to do again because the sound was gone.
Oh, okay. So let's start using Homotopy IO. We'll start by talking about this sort of example. So I often use this as like a first example of categories to introduce to people. So it's good for programmers. So like if you're doing functional programming, the idea would be that what you have is a load of sets. So in this case, we have a set of words and a set of numbers, and we have some functions. So this one would give us the length of a word, and this would multiply a number by 2. And then we can, of course, compose these arrows. We can get a word and then find its length and then times it by 2. So maybe we could call this double length. So let's see how we can encode this thing in Homotopy IO. So what do we do? So all we have to do, and I'd encourage you to follow along, anyone who's
I can start it myself too. Is that smart?
you can start it
Because
yourself as well.
I have an extra screen.
So what we really want to do is to visualize this kind of information. And I mean, this is really the coolest thing I want to talk about is Homotopy IO, because it's like it gives us the ability to talk about things like higher category theory in a arguably in a more sophisticated way than some of the best mathematicians that have come before us, and we can do it without any prior knowledge. So it's a really wonderful thing to learn. So how do we encode this in Homotopy IO? Well, basically, we want to make this kind of picture. So let's go. So if we go to this website, homotopy.io, this is all we have to do is run this. I'm running it in Chrome. And once we're here, we can just point and click and we can start building. So, are you?
Yeah, I look.
Yeah, great.
I watch, and then I can do it too, probably.
Great. Okay, and I'd encourage people watching to follow along if they like, because it's a really easy thing to get into. So this is what it looks like when we get into Homotopy IO. And pretty much the only thing that we can do to begin with is to produce a zero cell. So if we click on this plus button here, it makes a zero cell.
Mm-hmm.
And you see this has a name, it's called cell 1. So
Mm-hmm.
we want to rename this, and we're going to call it word. This is going to be our sort of object that's going to represent our words.
Yep.
And now what we want is to make another zero cell. So if we click plus here, it makes another one, and we can call it number. And so
Yeah.
let's go back to the picture and let's remember what we're trying to do here. What we want to do is we want to make zero cells called word and number, and then we want to make these these one cells, which are called length and times 2. So let's start by making length. So if we look at this, we can see that the source of length, where this length arrow comes from, is word.
Mm-hmm.
And the target of length is number. Mm-hmm. So this is like, we need to encode this in Homotopy IO. So all we do is we want to make this thing called length that goes from word to number. Mm-hmm. So the source should be word.
Yeah.
So we click on the pictogram for word, and it appears here. And then we say this should be our source. So we click this button called source. And now we click on the pictogram for number,
mm-hmm.
and we click target.
Yeah.
And now you see this has made a one cell.
Yeah. Yeah.
So we give this a name, we call it length.
Yeah.
And then we want to make another one cell, which is our times 2 thing. So that should go from number to number. So if we click on number, and then we click on source, that tells us that the source should be number. And then we'll click on number again, and click target.
Oh,
and so now we've made a one cell, which we could call times 2, which has a source as number and a target as number. And so now let's just have another look at our picture. So what we want to do is we want to do length, and then we want to do times 2. So if we go back to Homotopy IO, we can click on the pictogram for length, and you see it shows us the picture here. Mm-hmm. And we can see that if we hover our mouse over it, we can see that the source is word, and the thing is called length, and the target is number. And then if we click on the right-hand side, it composes. So now, after we do length, we do times 2.
How did you do that? Because I was looking for, because it didn't give me the text, the name.
Right. So what I did, I'll clear and start again. So I started by clicking on the pictogram for length.
Yeah.
And then click on the right-hand side of this orange line here. Then Homotopy IO realizes that it should try and compose with something. Yeah. And this is the only thing it can do. And so it gives us this composition. Okay. So this is like the basics of Homotopy IO.
Yeah, that's a nice way to compose. Delete overlaps. So that is what in the code is. Delete overlaps. That is what it does here too.
Yeah, it's a lovely way to compose because it's
do you understand what I mean?
No.
No, that because the one thing is the length, and the length has this a part which is called number. That is what this length is. And there is something else, and that is times 2. And that is that times 2 function, but it has also another part, and that is its number. And those number and number, those go together because they are the same, not just similar, but the same as
Yes.
as a thing. Because of that, you do not see it as two things upon each other.
That's a very interesting way of looking at it. So,
and that is very important notion, because otherwise this line or segment cannot be one-dimensional. It should be, because otherwise it would be immediately two-dimensional, because then it are two lines upon each other or next to each other.
And you were calling it overlap, right? So I guess what you're saying is that we can overlap this with this.
No, the overlap is in between the two vertices.
Yes.
That is the double thing is
here, right?
Yeah, that part is
exactly.
That part both have, and that is the overlap, and that overlap is important to know that it is there, because otherwise you do not understand what length is as you have defined it in this symbolics.
Exactly. So I was talking the other day with someone who does sort of technical programming, and it was really interesting. He was telling me about Linux. And did you know in Linux they have this, they call it the shell, and it's something that can run programs, and you can run any program, and then you can make sort of text as the output, and then that can be used as the input for another program. And so you can do one program and then another program. Now, in the shell, you can often do pretty much any program after any program. Whereas here, like you say, we have to have this certain kind of special overlap, right? Like,
yeah, well, because what is the same is the same in this thing, which is needed to get a word with a double number of letters, right? Or whatever.
Exactly. So here we're sort of, we want things to match up at the boundaries. So this is, yeah, this is like, this is important for, it's sort of, it's a funny thing. We're limiting what we can do in a sense, but it helps because we know what we're talking about. So what I want to do now, because at the moment, this is just like an ordinary category. Now we want to go to the world of two categories. So we're going to make this a bit more interesting. So if we have a look at this picture, this is the kind of idea that I want to encode. So imagine we're doing computer programming. And so we say, okay, I can have a word, I can have a number, I have this function that converts words to numbers. I have a couple of other functions here. One of them is this times 2 function. We've already seen this. You know, already with what we've got here, if we go back to Homotopy IO, we could think about some sort of programs, like say this one here, gets a word as an input, and then it keeps it gets its length, gets the length of our word, and then it keeps timesing it by 2. So this would give 8 times the number of letters in the word. But what about if we want to sort of compare programs? So let's have another program or function or procedure, whatever you want to call it, let's call it times1. So it goes from number to number. So if we click on number, say that's our source, and we click on number, and that's our target, then let's call this times1. Now I'm just going to change the color of this to blue.
Okay.
You don't have to do that, but it's just to match up with the drawing.
That's fine with me.
So
I liked it that it was yellow also, because then it is indeed so the same multiplied by the same, right? Times one.
Yeah. I shouldn't have messed about with the colors, but so what we want to do now is we want to start thinking about how we can compare these different programs. And in particular, like when you run programs, some programs will run faster than others. For example, like it's probably faster to times a number by 1 than to times a number by 2, because you don't have to do anything if you're going to times it by 1. So we can have this 2-cell here, and let's say this indicates that there's a sort of comparison between these functions. So I call this 2-cell as fast as. So timesing by 1 is as fast as timesing by 2. So let's draw that in. So this is interesting here, because what we want to do is make a 2-cell that goes from times1 to times 2. So we click on times1 and we say this is our source, and then we click on times 2 and say this is our target, and we'll call this as fast as, and I'm going to make it.
Okay. Yep.
So here we have our 2-cell. So this is sort of the beginning of the non-trivial bit, and it's a really things start to get very interesting very quickly at this point. So what's going on here? How are we supposed to read this picture? Well, we read it from left to right and from bottom to top. So we say that this black thing here is called as fast as, and its source is times1, and its target is times 2. So we're reading from bottom to top. And just to complete the picture here, what I'm going to do is click on the left-hand side of this, and then Homotopy IO asks me if I want to make an attachment. And
I'm sorry, I was a bit dreaming in the picture.
Oh, it's okay. Yeah, I know there's a lot going on here. So what we do is we take this picture. I'll just clear. We'll start again. So we'll click this 2-cell here.
Yeah.
Now, what I want to do, I'll click on the left-hand side inside this orange region here. And Homotopy IO says, okay, you clicked on me. You probably want to compose with something, but it doesn't know what should be composed, because many things can go there. So it brings up this attachment thing, and it asks us which kind of thing we want to lay down. What we want to lay down is length. So we click on length. Now we have this here.
Yeah, cool.
So if we go back to here, we can see what's going on here.
Yeah.
We've just made this picture on the right, and this picture on the right is sort of equivalent to this cellular diagram on the left.
Yeah, very interesting. It just has to get into my mind.
Let's go a bit further, right? So
yeah, please go on.
So the question really is, what's going on? in this situation. So we can come at this from a couple of ways. One way is, personally, because I've done a lot of category theory, I'm quite comfortable with pictures like this one on the left. And I could sort of think, well, what does this mean? Well, one way we could think about this is we could say that length, this length function, we could say that there's a sort of identity two cell like this. And if we're interpreting our two cells as meaning like as fast as, then computing length is as fast as computing length. Yeah, I mean, it's the same thing, right? So we could say we have this kind of two cell like this, but we also have this two cell like this. So that's doing times one is as fast as doing times one. So before I was talking to you about this idea of composing two cells. So I said, if we have two cells like this, then we can compose them so we get these two things are kind of the same, right? In other words, we've got these two and we compose them to make a big two cell like this. So that's called vertical composition of two cells. It's like doing one two cell and then doing another two cell. But there's another way that we can compose two cells. Which is, it's called horizontal composition. So the idea is that when we have them horizontally next to each other, then we can interpret that as a sort of big composition like this. Now, in this picture, what's it mean? It means that we can say at the top here, we're going to have, okay, I should use different colors. We're going to have length and times two. At the bottom, we have length and times one. And then we're saying that doing length and then times two is going to be as fast as doing length and then times two. Sorry, we're saying doing length and then times one is as fast as doing length and then times two. So this is the sort of horizontal composition of these two cells. So
I understand what you mean.
Okay. So this would be a nice thing, I guess, about this as fast as thing, right? Like, you know, we can sort of apply it in parallel. But the other thing then, now we understand what this means. The question is, how do we convert it to this? So this is another one of these sort of duality things. And it's really the central idea. The idea is that if we think of this picture here as directed, so it's directed from left to right and from bottom to top, then these two pictures here have the same information. Like, how do they have the same information? Well, what we can do, if we want to convert this one into this one, wherever we have a two-dimensional region, wherever we have a two-dimensional region, we'll make a point. So these become points. And then wherever we have a line, or an arrow, we'll draw a line that's sort of perpendicular. So we end up drawing a picture that looks like this.
Mm-hmm.
And we don't really bother drawing this as a dot because this is an identity. And so what we've basically drawn here is these two vertical lines, which correspond to these. And then this 2 cell here as fast as becomes this 0-dimensional thing. And these objects here now correspond to these 2-dimensional regions.
Mm-hmm.
So basically what we're doing is we're changing the 0-dimensional stuff to become 2-dimensional, 1-dimensionals becoming 1-dimensional, and 2-dimensionals becoming 0-dimensional.
Mm-hmm.
We can also go the other way around. So if we have this, we can convert it into a cellular diagram. So we can go, these become objects, and then wherever we have a line, we draw an arrow which is perpendicular to it, and this becomes a 2 cell.
Mm-hmm.
And that lets us go.
Because then the purple vertical is then not a 2 cell, because that is a 1 cell, just a line, and the
Exactly.
other.
Exactly. So this is something pretty interesting.
Because then the one thing is a line composed of as just line. I am a kind of eternal infinite line, and the other is a line composed of 2 lines starting somewhere, and that's that 0 point. They have the same beginning.
Exactly.
And the one goes that way, the other goes that way.
Exactly. And this is one of the nice things about this kind of manifold diagram way of doing it, that it gives us this nice way to think about identities. Let's push on, because if we look at examples, we'll get more ideas. So right, let's our next example then. Okay, so this is a really simple one. So the idea here is that we're just going to think about how we can make words or kind of combinations of A, B, A, B, A, B. We can write words like ABBA. So it's a very simple thing, but it's nice to think about. So if we go to Homotopy.io, let's start a new session. So I'll just make a new window. And now we're just going to have a single 0 cell that we'll call star.
I have to go to put it all away.
Yeah, if you just make a new tab and then go to homotopy.io, that's the easiest way to do it.
Okay. Yeah, I see. Okay. Yeah. Yeah. So okay. We make a
cell. A 0 cell. Let's call it star.
Okay. Yeah.
Now we're going to make a 1 cell, which is going to have star as its source and star as its target. And let's call that A.
Yeah. Little a.
Yeah, little a.
Okay.
And now we're going to make another 1 cell that has star as its source and star as its target. And we'll call it B.
Okay. Yeah.
And that's all we want to do. So if we click on the pictogram for A, we could say A is an arrow that goes from star to star. And then if we click on the right-hand side of this red line here, Homotopy IO asks us what kind of thing we want to attach. So let's attach a B.
Yeah.
And then we can click on the right-hand side and click B, and then click A, and so on. So now we've got ABBA, A, and then B, B, A. So this is pretty simple, but like we can ask sort of what's going on here. And another way we can visualize this, which is
now I have ABBA. Now it does it the field where the pointer does it do since the signal is not always super.
Yeah. So okay. The way that we can sort of visualize this is we could say, well, what we have is a category that just has a single object, which is called star. And we have these arrows called A and B. And then there's various other arrows like A, B, B, A, and all of these different things. So this is what we call a monoid in in mathematics. It's just a category that has one object.
Yeah.
So this is where we get to the really, this is like, I love this so much. It's John Baez is one of my favorite popularizers of category theory, and he has various articles and videos where he talks about this thing called the periodic table of n categories. And it's like this way that you can think about n categories. And it's like, personally, I think I could think about this thing for like a year straight. It's so interesting. And so let me show you this table. Can you see something green here, Jos?
No, I see this part text in purple, what you have written yourself, and a part of this table.
Great. Okay, then. So what on earth is going on here? There's a lot suddenly appeared. So let me start to explain. You see here we have this table, and it has these different columns, and they're labeled by n. So this would be n is 0, n is 1, n is 2. And then also we have these rows, and these are labeled by k. So k is 0, k is 1, k is 2, and so on. So the idea here is that, okay, so let's start by looking at this first row. What's going on here? So here we have k equals 0. Now, haven't told you what k means yet. We'll get to that later. But when n is 0, what we have is a set. So let's draw a picture of a set. It's like a bag of points. Yeah?
Yeah. I listen.
Okay. And then when n is 1, we have a category. So now we have these objects, but we also have arrows between the objects.
Yeah.
And then when n is 2, we have a 2 category. So we have these 2 cells.
Yeah.
And we can go on and on and on. So here we would have 3 categories, and then 4 categories, and so on. So that's what the top row of this table is. Now, then the question is, well, what's k? I mean, I've just told you about this k equals 0 situation. Well, what k is it's the number of dual layers. So when I say a dual layer, I mean it's a layer where we only have a single thing. So you remember before, in the last example, we only had a single zero cell, which was this star. So we decided to sort of restrict our structure like it was a category, but it was sort of dull on the zeroth layer because we only had a single zero cell. And then we had something a bit more interesting after that. We had lots of A's and B's. And so you see here in the table, when k equals 1 and n equals 0, what we have is a monoid. So a monoid is like a category, but it's dull on the first layer. So what I mean is we have only a single object, and then we have like A and B. So
yeah,
this is the idea of a table. So more generally, here's the definition. The thing that goes in the place n comma k is what we call it's called a k-tuple monoidal n category.
Oh, that's a nice word.
Yeah,
a k-tuple monoidal n category.
exactly. And what it means is it's like it's a n plus k category, but the first k layers or levels are dull. So we'll see what this means, right? So basically the idea is like this. If you get a category and it only has, but you get a category that only has one zero cell, then you get a monoid. Another thing you can do, let's say you want to cook up something in here. Let's use a different color. Let's say you want to get something in here. So what should this do? This should have, we've got n equals 1 and k equals 1. So what's this mean? If we read this definition, then what we should have is a 1 plus 1 category that's dull on the first layer. That's just reading this definition. So what this is this is a 2 category that only has a single zero cell.
Okay, it's go on.
Yeah, I mean it takes a while.
I understand what you say, but
okay, good. So let's take a look at an example, then it will become clear. So we've got a nice example. Here. Okay. So this is our example when n equals 1 and k equals 1. So what's going on here? Well, we just have this sort of background thing, which is called star. What we're talking about here is multiplying numbers. So we're going to have two numbers, 0 and 1, and we're going to think about multiplying them by each other. So the purple is 1, the orange is 0. This says 1 times 1 is 1. 1 times 1 is 1. This says 1 times 1 is 1. And this says 1 times 0 is 0. So we can talk about arithmetic, right? This is what we're going to do here. So
but my question is here: what is the meaning of the white point and the black point? in it, in the reading, how to read
Yes.
it. There is a field, and that field is called numbers. That is the red field. And then there are specific numbers, and one is yellow, and that is called 0, and there is one that is called purple, and they do something with each other, and that is times, you say.
Yes, exactly. I mean, honestly, this is what it is, and it could represent different things, right? So we can have many interpretations for this, but the interpretation I'd like to have is that the red is just a sort of background. We don't have to call it number, we'll just call it star. So it's just a background. Okay. You know, like I was trying to illustrate this idea of these k-tuple monoidal n categories. So the idea is that they're dull on the low dimensional layers.
Yeah.
Much like in this case with the A's and the B's, we just wanted to be able to put any letter next to any other letter. So we only have a single 0 cell. So it can allow us to push everything together. In a similar way, we just want to have this star thing as a sort of background. But then we have two different kinds of one cells. They're one of them's called 0 and the other one's called 1. Mm-hmm. So you were asking, what do these black and white dots mean? So the idea of this black dot is you should read these from bottom to top. So it takes in a 1 and a 1 and it outputs a 1. So it's saying 1 times 1 equals 1.
I understand.
Yeah. So yes. So there's a couple of ways you could interpret this. You could say it just means times, right? So if we feed in a 1 and a 1 and we times them, 1 times 1 is 1.
Yeah.
Or you could say it's an equation, right? So it's this sort of equation that's saying 1 times 1 equals 1. I mean, it's probably
you could also call him true and the white one false.
What 1 is true and 0 is false. That's exactly right, Jos. Yeah. You want to say more about that? Because
it's of course in the yellow one, then yellow comes to white, and then it goes to the right, and then the white is right. True.
Yeah, exactly. So we could say this means true, and the yellow means false, and instead of times, this could be and. Right. So true and true is true.
Yeah.
True and false is false.
Yeah.
So
yeah.
We're doing logic.
Yeah.
Okay. So let's have a look how we can encode this then.
Okay.
So if we we'll start a new one. So let's go to Homotopy IO.
Yeah. And we call that cell?
Let's call it star.
Star. Yeah.
And now we're going to say that 0 has star as its source and star as its target. So it's a one cell that goes from star to star.
Yeah.
And the same with 1. Okay, so I want to get that multiplication symbol. So I'm going to Google for it. Be that?
Yeah.
Okay. So now if we go back to our thing, we want to have some equations, right? So we want to say 1 times 1 equals 1.
Mm-hmm.
So that, let's talk about this, okay? Or we could say it's the same thing as this. Do you see how these are sort of dual to each other?
Mm-hmm.
Like we could convert this one on the left to this one on the right by sort of dualizing it right that, right? Anyway. Okay, so let's go back to Homotopy IO. So we want to say that if we start with 1 times 1, then we can get 1. So we'll click on the pictogram for 1, and then we'll compose it with 1. So we attach 1 to the right-hand side.
Yeah.
That shall be our source.
Yeah.
Now we'll click on 1, and that shall be our target.
Okay.
And now we'll call this 2 cell here. I'm going to call it 1 times 1 equals 1.
Yeah.
I think I'm using a different color scheme to my picture, but anyway.
No.
Right, and now we can just do similar stuff.
Yeah.
With the rest of it. So let's say 1 times 0 equals 0. Okay, so we click on the pictogram for 1. We click over here. We click 0.
Yeah.
We say this is our source.
And then we get 0.
And then we click 0, and then we say target.
Yeah.
And now we could call this 1 times 0 equals 0.
Yeah. Okay.
And now what we can do is put these together, right? So we can sort of make, we can do arithmetic basically. So if we click on the pictogram for this 1 times 1 equals 1,
Mm-hmm.
now let's click on the left-hand side in the red. And now Homotopy IO says, okay, I can attach something here, but I could attach 2 different things. I could attach
0 and 1.
a 0 or a 1. So let's attach a 1.
Okay. Yeah.
And now, if we click on the, let's click on the top between these 2 purple lines, and we get this.
Yeah, because it's still the same.
And so what you're looking at is a proof that 1 times 1 times 1 equals 1. Right? Because at the bottom, 1 times 1 times 1. And then we use this equation. So now we've got 1 times 1. And then we use this equation. And then we've got a 1.
Yeah.
Or if we click on the right-hand side, let's put a 0 on here.
Yeah.
And then if we click on the top,
Mm-hmm. Yeah, then you have that 1 times 0 is 0.
yeah, so if we read the whole thing, it's a proof that 1 times 1 times 1 times 0 equals 0.
Yeah. Yeah. Yeah, the final outcome is 0.
Yeah, exactly. Or we could say true and true and true and false equals false.
Yeah. Yeah. Yeah, indeed.
I really love this because it means that like we can think about so many things to do with maths in terms of shapes now.
Mm-hmm. Yeah.
Okay.
Yeah. Okay.
Okay. So what we've been
I've a word. What is tuple? Does that mean something?
yeah, it's like many times. So like one tuple would be once, two tuple would be twice, three tuple would be three times. So the idea is that a monoidal category you could kind of think of as like a high dimensional structure, but it's just dull on the bottom layer. So it only has a single zero cell. But if it's two tuple monoidal, that means it's dull on the first two layers. So it only has a single zero cell and the identity of that zero cell. And then we start building interesting stuff on top of it. So there's kind of like how many times it's monoidal in a sense. So we've been exploring this table. So we've seen sets, we've seen categories. For example, that length and times two thing. We've seen that two categories, like that one with as fast as. We've seen monoids, like that ABBA thing. And now we've just seen a monoidal category. That was like a two category with one object. That was our timesing 0 and 1.
Mm-hmm.
Now let's take a look at something here. So this is k equals 1 and n equals 2. So what this is going to be is it's going to be a 3 category, but only with a single 0 cell. So it's dull on the first layer. So here's our picture of it. It's three-dimensional now, so it's getting a bit more interesting. So I think the easiest way to understand this is just to start drawing it. So we'll start a new window, .io.
You did it like that. That is also smart. Yeah.
So dull on the first layer. So we just want a single 0 cell that will call star, the usual thing.
Yeah. Yeah, cool.
Okay, so now we're going to have a 1 cell that has star as its source and star as its target. Let's call it A, capital A.
A. Yeah.
Okay, so we're going to be abstract, Jos. We're going to just imagine that there's something that takes in a couple of A's and then outputs an A. So we'll click on A and we'll compose A with A.
Yeah.
And we'll say that's our source.
Yeah.
And we'll click on A and we'll click target.
Okay. Yeah.
Let's call this multiply.
Not just X.
Now we'll call it multiply because it could be something more abstract. It could maybe A represents numbers and this is numerical multiplication, or maybe it's some more abstract thing, like it could take in two dogs and put a dog or something. So if we click on it, we can see that multiply takes in an A and an A and it outputs an A.
Yeah.
And if we like, we can do things like if we click on the bottom left, we can compose. So now we start with three things and then we do multiply and so on. Okay. Now what we're going to do is make another thing. So a good question to ask at this point is, how many two cells do we have? Well, sorry. A good question to ask at this point is, how many one cells do we have? And we have this one cell called A, and then we can compose it so we can get AA and AAA and blah, blah, blah. We also have something where we have no A's at all, which is just red. And that's the identity of star. So if we click on star,
and
then we click identity, now we have this one cell. It's called star. So in a sense, this is like the sort of absence of A's. We have our background star, but we have no A's. And we could say that this
is a nice kind of zero.
Right, yeah, exactly. It's some kind of yes. It's like a zero or something, or a sort of
source, the origin.
It will be for us, yes, because what we want to do is think about what it would mean to make an A out of nowhere. So our source shall be this, and our target shall be A. And we're going to call this unit. And so now what we can do, if we click on multiply, we get this pictogram. And now if we click on the left-hand side, we can compose it with unit or attach the unit. So we can then ask, what does this mean? What's going on here?
That is multiply a unit, and that must give some kind of multiplication.
Right. So if we read it from bottom to top, just sort of interpreting it literally, we start with an A, and then we use this unit to make another A. So now we have an A and an A, and then we multiply, and then out comes an A. Now,
but then it disregard that one A and the other A is some kind of A, some kind of itself. It's also a delete overlap in the outcome, in the sum.
Yes, exactly. Things are matching up. Now, there's a reason why I called this unit, and it's because I want to think about this as something that if you multiply with it, it doesn't do anything.
Okay.
Now, there's no reason why you should believe that just from this picture. So to encode that it doesn't do anything, we need to add an equation in. And the equation is basically that if you take something in A and the unit and you times them, it's like you didn't do anything at all. Right? So it's kind of like 1 times a number equals that number. Now I want to encode that as a higher dimensional cell. So let's have this picture here as our source. And now we click A. And we click identity.
Yeah.
and we click target.
Wow. And how do you call it?
Let's call it equals.
Yeah. Yeah. I like that's a good name for it.
So if we click on it,
Yeah.
you see we can render it in 2D, but let's render it in 3D. So here it is.
Yeah.
So what's going on here? We should read it from sort of right to left, if you like. So what we start with is the unit and the multiply. And then what we're saying, and that's like the front part, the part that looks like a Y. So you sort of imagine slicing it at the right-hand side. Then you're starting with that thing that we started with, where you've got your unit and then you're multiplying. That's like the front sheet of this. That's this stuff over here.
Yeah.
And then at the back, we just have the identity of A. And then the sheet itself, or the 3D block, is saying that the front part equals the back part. So it's saying if you're, okay, it's better actually if we go back to 2D, and then we can look at this thing slice by slice. So if we vary the slice, we start it as source. This is what we start with. We start with the unit multiplied by A, and then we get A out. And then that's our source slice. And then our target slice is the identity. And so somehow we're relating those two different things. And so you can go through it slice by slice.
Yeah, yeah, yeah.
And that's this 3D picture.
Okay, go on.
Okay.
Go
So
on.
what's going on here? Well, you know, we've been using this kind of duality to understand what's happening, right? So we saw different kinds of duality. At the beginning, we saw this duality where we swapped around. We started with this sort of one-dimensional thing, and we swap around 0 and 1 dimensions. Then we get this case here where we have like a two-dimensional thing, and we swap the dimensions of things like this to go between these two different pictures.
Yeah.
Now we do the same idea, the same kind of Poincare duality, but now at a higher dimension. So the zero-dimensional things become three-dimensional, the one-dimensional things become two-dimensional, and so on. And by doing this, we swap between these two different pictures. So this is the sort of cellular picture, and this is the sort of manifold diagram picture.
The red thing is that because you in the left in the category thing you call the ID the red arrow.
Yeah,
and you have the red dots.
That's right. So this red dot is what we've been calling star.
Okay. And
now,
and
if
that's
you look on the right-hand side, because star is a zero cell.
Yeah.
On the left-hand side, it's zero-dimensional.
Yeah.
Once we've applied this duality, on the right-hand side, it should be three-dimensional.
Yeah, but why is it not red?
Well, imagine this is like imagine this sheet is dipped in red paint. So this is like a three-dimensional sheet, right? Or it's a kind of sheet with a little bit of a flap.
Yeah.
Imagine you took this and you dipped it in red paint.
Yeah.
Then it would be separating a red 3D region on one side and a red 3D region on the right-hand side. There would be a load of paint over here and a load of red paint over here. And this sheet would be a sort of membrane which would separate these two 3D regions of red paint.
Yeah. Okay. Yeah.
And those correspond to these. You could say, actually, why are there three of these and not two? And it's a bit of a funny trick. What I kind of did is I sort of said, well, maybe we can think of this part here as a sort of extra 2D membrane, but because it's an identity, we don't have to draw it. And now we have a red 3D blob here, a red 3D blob here, and a red 3D blob here. And those correspond to this, this, and this.
Yeah. And because of that, yeah.
Now, the next part is we then say, okay, what's the next rule? We have these one-dimensional things. Yeah. And according to our rule, those should become two-dimensional. Oh, it's like a smiley face. I mean, the truth is that the best way, probably the reason it's confusing is that we should really draw this thing on the left as if it's like a sphere. And what I mean by that is we should draw it like this. We have part of it, but then we should also say that on the back we have A, and then we have A, and then we have the identity of A. And then if you imagine this like a sphere, this would be like one hemisphere, and this would be the other hemisphere on the back. And then in the middle of the sphere, we have this sort of 3-cell here, which is called equals.
Mm-hmm.
And so what we're saying here is that this composition here, which is this stuff here, is equal to the stuff on the back of that 3D picture, which is this. So in other words, equals is declaring that this stuff on the front is connected to this stuff on the back. And so that equals is like this 3-cell here that goes like that. Is that making sense?
Yeah, no, it makes also sense that because of the equals shows what is equal.
Yeah.
So everything is equal except that there is a unity and something that multiplies and that comes together in some kind of dot, and that is, and it happens all in the equal.
Yeah.
So they're in the domain of equal.
Yeah, that's it. And then it's lovely because we can use these kind of 3D pictures to represent sort of equations, as you say, and then we can put them together to do more complicated reasoning. Like, for example, I'll just quickly go through this. If we multiply, let's go 2D. So we could multiply like this. So here we multiply, we have three things, A, and A, and we start by multiplying the first two, and then we multiply that with the other one. But maybe if we do it the other way around, it's the same. So we could say that this is the source. And this is the target. And these things are also equal. So now we have this 3D sheet, and it's saying that if we multiply the first two things first and then the last thing, that is equal to what we get on the back sheet, where on the back sheet we multiply, if we spin it around, maybe I shouldn't spin it, but then we multiply the first thing, well, we multiplied it, thing number 2 and thing number 3 first, and then we multiply that with the first thing. And this is saying it doesn't matter which way around we do it. So if we look at it in 2D, the first slice is this, the front slice, and the back slice is this, and we're saying now that these two things should be equal.
Mm-hmm.
Okay, so in order to get a bit further exploring this periodic table of n categories, I want to be a little bit more precise about what an n category is. I haven't been very precise at all so far, but a good way to think about n categories is to think, I mean, this isn't really very exact, but to think that there's something like a sort of spectrum. And on one end of the spectrum, we have strict n categories. And at the other end of the spectrum, we have so-called weak n categories. Now, strict n categories are simpler. They have more precise, they have more constrained rules. And they're basically the kind of things I've been hinting about so far. So the idea is that we can have one cells and we can compose them, and it's associative, and we have a unit and we can use that, and maybe we have two cells and we can compose them end to end and they're associative, or we can compose them side to side horizontally. And then with the two cell structure, we come to our first kind of interesting equation, which is what I'm showing here. So the idea is that if we have a couple of two cells which are side by side, then we can horizontally compose them. We could also horizontally compose these. And so when we have 4 two cells arranged like this, imagine that this arrow is the same as this arrow, and this is the same as this. Well, then, when we have this sort of situation, we could compose these two first. So the idea that I'm trying to illustrate here is that when we have two cells like this, so we have alpha, but after alpha dash, horizontally composed with beta, after beta dash, with these general two cells, well, there's a couple of ways that we could think about composing them, right? We could compose these two first horizontally, and then we could compose those vertically. So that would be, as I'm trying to illustrate in this picture, or we could compose these things vertically first and then compose the results horizontally. And what's interesting is that we have this kind of interchange law, which is telling us that these two things are the same. Now, this makes total sense with the way that you would arrange this kind of thing in Homotopy IO. Because in Homotopy IO, you'd just be drawing some sort of a picture that looks like this. And it's sort of clear that you're free to read it as like this side by side with this, or you could read it as this on top of this. But anyway, this is our interchange law. Now, one thing that's interesting is that, so that's our interchange law. And so I've given you a sort of outline of the idea of a strict 2 category. Now, if you want to understand strict n categories, I would say, in my opinion, the best way to do it is to do it using enriched category theory. So I have a video on enriched category theory, and the idea, very, very roughly, is that in an ordinary category, you'll have a set of arrows from A to B. But in enriched category theory, you might have something more general than a set of arrows from A to B. Instead of a set, it could be some object in some more general monoidal category. In particular, we might have something like this. And so instead of having a set of arrows from A to B, what we might have is a category of arrows from A to B. So this category has 3 objects, F, G, and H, and it has arrows as I'm showing. And so if we think of a category enriched category, rather than having a set of arrows from A to B, it has a category of arrows from A to B. And it turns out that a category enriched category is the same thing as a 2 category. So, and then the pattern continues. There's a category of 2 categories. We call that 2 cat. If we enrich in 2 cat, we get the idea of a 3 category. Then we can get the category of 3 categories. We call that 3 cat. And we can enrich, and something that's enriched in 3 cat is a 4 category, and so on and so on. So we can get at strict n categories by repeatedly enriching. We start by enriching in sets to get ordinary categories. Then we get cats, the category of categories. Then we enrich in cat. Then we get members of 2 cats. Then we get 2 cat. Then we enrich in 2 cat. We get and so on and so on. So that's the basic idea of strict categories. But what is interesting and kind of complicated about higher category theory is that we also consider these sort of weakened notions of n categories. Now, it took me a long time to appreciate why people do this, because it really it makes things more complicated. It doesn't really matter for us because we're just taking a sort of intuitive glance at these ideas. But basically, the idea of weak n categories, well, a weak 1 category is just a 1 category. A weak 2 category is what you call a bicategory. Now, a bicategory is kind of like a 2 category, but some of the parts of it don't work in quite such a constrained way. To be more exact, a bicategory has all the same kind of stuff as a 2 category. It has 0 cells, 1 cells, and 2 cells. The difference is in how composition works. So ordinarily, if we have a category and we have 3 sort of composable arrows like this, then we're going to have this associative law. So we're going to have that H after GF is equal to HG after F. That's just the ordinary. That's just the ordinary associative law. But what happens in a bicategory? And I'm just sort of giving a rough idea of the thing. The basic idea is that instead of having this as an equation, we have this as a sort of natural isomorphism. So we're going to have these 2 cells which are invertible, which allow us to convert between H after GF and GH after F. So basically, a bicategory is like an ordinary category, except the associative law and the sort of unitality, this idea of composing with a unit giving identity, those don't work on the nose. They work up to a higher dimensional cell that's kind of like an isomorphism. And then we go further. So there's the notion of a weak 3 category. Again, we have some sort of weak associative laws. In fact, at that point, we can get even more relaxed about things, because once we get to the idea of a weak 3 category, these kind of built-in equations that we had at layer 2, we can relax. So in a weak 3 category, we could say that this interchange law is not actually an equation anymore, but it just holds up to a sort of higher dimensional isomorphism. So there's going to be, we're not saying that these two things are equal anymore. We're saying that there's going to be a sort of invertible 3 cell between this and this. And that's the kind of thing that's happening in a weak 3 category. Now, the reason all this stuff gets complicated is because what we're doing is, as we're sort of making these weaker, higher dimensional categories, we are taking the equations that hold at lower dimensions and saying, no, they're not equations anymore. These are just holding up to some kind of canonical isomorphisms. But we want to have these things as being well behaved, meaning that when we use them in different ways to convert one thing to another, those different ways should agree. And to get those things to agree, we need to add in some sort of coherence laws. And this is where things get complicated. So if you remember in the definition of a monoidal category, as I speak about in another video, there are these strange kind of coherence conditions, like that this pentagon diagram has to commute and things like that. And those kind of things come about, and you sort of gather more and more of them as you go to high dimensions using this idea of a weak n category. Now, I'm quite interested in weak n categories because of the connection with topology, in particular fundamental n groupoids. It's something I'll talk about later, but they're interesting, especially related to sort of homotopy theory or homotopy type theory. But also this homotopy IO thing's interesting. And so it's interesting to consider another sort of point on this spectrum here, something that we could call a semi-strict n category. So more in particular, the kind of structure I think is particularly cool is something which is called an associative n category. So this is not a strict n category, but it's also not as weak as a weak n category. The idea here is that we do have some of these equations from here relaxed to become these sorts of higher dimensional isomorphisms, but only those which are based on things like interchange laws. This associative n category, it has associativity of composition on the nose, and it has unitality equations holding on the nose. What it doesn't have holding on the nose is things like this interchange law. If we're looking at an associative 3 category, then this interchange law, for example, is only going to hold up to a higher dimensional kind of isomorphism. So these associative n categories are a really nice middle ground, and they're quite recent discoveries. So there's a very interesting PhD thesis by Christoph Dorn. And he talks a lot about these associative n categories. The punchline basically is that Homotopy IO is designed to handle these associative n categories. And essentially, you can think of them in some sense as the kind of things that you can build using Homotopy IO. So if you look at this lovely thesis, let me see if I can find some nice pictures. Right. So if you look at this lovely thesis, you'll see that basically this idea of these associative n categories is the same kind of thing as what you can build in Homotopy IO. And so in a sense, you can almost model the idea of the associative n categories from the kind of things you can do with Homotopy IO. So there's this lovely thesis, and also there's some papers on zigzag categories, which are the kind of constructions that you use to set up the data structure behind Homotopy IO. Basically, the idea is that something like this picture on the left in Homotopy IO could be represented by this kind of zigzag pattern on the right. And you'll have to have a look at some papers like this one here if you want to know more about this. But anyway, now we've unpacked a little bit more of this kind of n category theory, I'd like to return to this table here, and let's go a little bit further into this table. So in particular, I want to have a look at this. So this is interesting. This is the case where we have n is 0 and k is 2. So we have sort of an n plus k category. So that means it has layers 0 all the way up to k, but the first k of them are going to be dull. So in this case, we're going to have a 2 category, but the first 2 layers, as in the 0 cells and the 1 cells, are going to be dull. That means we're only going to have a single 0 cell and the identity of that. So let's cook up something like this in Homotopy IO. So we're just going to have a single 0 cell that we're going to call star. And now our next kind of interesting thing is going to be a 2 cell that goes from the identity of star to itself. So we look at star, we take the identity, we use that as our source, then we get star, we take the identity and use it as our target. Now what we're going to do is we're going to call this A. And let's go again. So we take star, ID source, star ID target, and we'll call this B. Okay, so what we have here is a pretty interesting structure. So we've basically got these kind of elements A and B. And if we were working at one dimension lower, we could say, well, you know, we can compose these things, we can put them we can put them next to each other. But what we can do in this situation is we can also put these things aligned vertically. Okay, so we can make a picture like this. So what does this picture represent? Let's take a screenshot. So all we're going to do now is just sort of dualize this picture. So maybe make it a bit smaller. And now we have the identity of star. So there it is, ID of star. Draw it 3 times. And now what we have is A, which we can think of as a 2-cell like this. And we also have B that we can think of as a 2-cell like this. But now there's something pretty interesting that happens here. And this is kind of a bit, well, it's a very interesting thing. Let's put it like this. So we can do a little bit of sort of trickery here. We can rewrite this. So here's the sort of trickery. It might take a bit of time to understand this, but this is something called the Ekman-Hilton argument. Basically, the idea is like this. Because we have this sort of twice monoidal structure, we have an identity, we have this single object star, and we have the only 1 cells we have are the identities of it. So we have a sort of picture that looks like this, and then these are going to be 2 cells. So let's call them A and B. Now, the thing is, there are 2 different ways that you can compose 2 cells. You can compose them head to tail, or you can compose them horizontally. And the thing here is that all of the boundaries that these things could have are the same, because we have this kind of trivial structure for the 0 cells and the 1 cells. It's dull on the first 2 layers, or k equals 2. So what that means in particular is, well, we're evaluating this, and one of the rules of these categories is that if we horizontally compose with an ID, it doesn't change anything. So we could replace this B with this horizontal composition here, and replace this A with this horizontal composition here. And now these things should agree. But then we can start to do some tricks, because we can absorb these identities in like this. These are both equal to B and A respectively. So we have this equation here. And then we can do a similar trick to rewrite this like this, and then rewrite this like this. And notice that we've been able to sort of turn upside down our 2 cells. We started with A and then B, and then we've kind of used the interchange law to swap things round, and now we have doing B and then A. And so if you think about this sort of composition, you can think of it like a sort of binary operation, right? Like that makes sense, because we can compose any 2 cell with any other 2 cell. And in that case, this binary operation, well, it turns out that it's going to be commutative. Okay, that's kind of what this argument is implying. It's saying that composing B with A gives us the same result as composing A with B. And it also agrees with doing the horizontal composition. So this is this sort of Ekman-Hilton argument, and it implies something pretty interesting. So if we go up to the category, our periodic table of n categories, what it says is that if we take a monoidal category with 1 object, or equivalently, if we take a sort of 2 category that's dull on the first, dull on the 0 cells and the 1 cells, well, that's going to look like a commutative monoid. So let's see if we can actually see this in Homotopy IO. So it's kind of easy to see in Homotopy IO. If we get this sort of vertical composition of A and B, then we can literally just drag these things around. And believe it or not, this corresponds to a sort of visual proof of this kind of usage of the interchange law to prove this Ekman-Hilton argument, to prove that we have a sort of commutative monoid here. Okay, so here's a particularly interesting entry in this table, which is this one, which is braided monoidal categories. So if you know about monoidal categories and you start to get into like the definition of things like symmetric monoidal categories, if you look them up on NCAT you'll find out about things called braided monoidal categories. Basically, the idea is that when you draw the wiring diagrams, you have this operation where you can braid one wire over another, and then there's connections with knot theory and so on. So what's a braided monoidal category? Well, firstly, let's ask what's a monoidal 2 category. And we can think of such a thing like that as just a 3 category with one object. This is just a 3 category. So we'd have 3 categories up here. And this is just a 3 category with one dull layer. So we only have a single 0 cell called star. Whereas here, what we have is a 3 category that has 2 dull layers. So we have this single 0 cell, which is called star, and then we have the identity of star, and that's going to be a 1 cell, and then we start building things on top of that, and we're going all the way up to 3 cells. So it sort of has 2 different kinds of things that are non-trivial. It can have 2 cells and 3 cells, but they're sort of built upon these 2 initial sort of dull layers. Easiest, of course, to have a look with, and with easiest to actually have a go at this with, the easiest thing to do, of course, is to go to Homotopy.io, and we'll visualize something like this. So we need our 2 initial dull layers. So we've got star, and then we'll take the identity of star and use that as a source, then the identity of star and use that as a target. So these are going to be our most basic building blocks, these sort of 2 cells that go from ID of star to ID of star. So we can call such a thing A, for example. Let's make another one. So ID is the source, ID is the target. Let's call this B. And at this point, you probably think that the setup is the same as the setup for commutative monoids. I mean, it is, because like if we have a look at our table, we see that both braided monoidal categories and commutative monoids in this table, they're both visualized as things where the bottom 2 layers are dull. The difference is that here, when we're talking about braided monoidal categories, this isn't as high as we can go. Okay, we can also consider 3 cells. And that's pretty cool because that makes us get at this notion of braiding. So I can sort of show you what I mean. So we have this set up here. Well, what we can do is we can take the identity of this. So now what we have is this 3 cell here. You can sort of think of it as a sort of world line of this orange and purple, these orange and purple particles. Now, if we go back to 2D, we can do something pretty interesting, which is that if we start dragging these, use a mouse. Right, if we start dragging these things around, so we just sort of point and click and drag these points around, you can see if we have a look at in the 3D case, what we're doing is we're sort of twisting these things around. So again, if we look back at 2D, if we go through this slice by slice, the source slice has the purple point above the orange point, but then as we go forwards with the slices, you can see that we've pulled this purple point down by 1. And then it's been pulled back up again, so we get to the target. Now, you can see that we've pulled this purple point down by 1. Okay, I'm going to clear. I want to show a different way of looking at this. So let's start again. So we get A. we put this point B on top of it. So here's another way that we can make such a braiding. So we're going to look at the identity of this again. So notice that when we look at the identity, what we essentially have is this 3-cell. That's why it's 3-dimensional, right? But it's a kind of boring 3-cell in a sense that, it's just the identity of something. But what we can do is we'll look at a projection of this down by 1 dimension. And now what I want to do is start braiding this. So I want to pull this purple wire. I'm just dragging it over the top of the orange wire. And now I'm going to drag the orange wire over the top of the purple wire. There we go. And so now what I've done is I've twisted these wires around each other. So let's have a look at this in 3D. And you can see now it looks like this. So what I've essentially done is braided these things. And so I've had this sort of 3-cell here, which I've been able to build just using the kind of deformations that come for free in this sort of structure. And basically what these deformations are applications of the interchange law. So this is an interesting point in our sort of development of N categories, because a lot of things are suddenly appearing at the same time. I mean, basically what we're seeing here is the appearance of knots theory, right? But just to understand this picture a bit better, if we go back to 2D, we don't project, then we'll just look at this slice by slice. So this is the sort of front slice. And then as I move forward slice by slice, you'll see these sorts of particles twisting around each other like this. And what's really going on in a sense is we're sort of looking at the world lines of these particles that are sort of twisting around each other in time. And then we're sort of slicing that block of time up and looking at it slice by slice. So what's really going on here in a sense, is we're looking at the interchange law happening. So remember with the commutative monoids, it was the interchange law that allowed us to be able to twist these things around each other or rotate them round. But what's going on here is that our interchange law is not holding exactly. So if we go here, this was what our old interchange law looked like for commutative monoids. So what this was basically saying is that if we're looking at so what this is basically saying is that if we're looking at a bicategory, and then we start looking at 2 cells that are identities of the identity, and then we start looking at 2 cells that go between the identity of star, then we can keep applying the interchange law, and we have these equations here, and these literally make it so that A composed with B is exactly equal to B composed with A. Okay. In terms of homotopy IO, this means that when you spin the purple and the orange dot round each other, it literally doesn't affect the outcome of that composition. But what's going on here is that we're not capping things at 2 dimensions. Okay, so we're not saying that these babies are the highest dimensional babies in town. What we're saying is that there are also 3 cells, and then because we're looking at a weak 3 category, okay, so here it's important that we're not looking at strict stuff. We're looking at a weak 3 category, and that means that this interchange law is not holding up to equality. It's just holding up to a sort of coherent natural isomorphism. So we're going to have these sort of invertible 3 cells, which look like this. And basically what this is saying is that yes, you can twist A and B round each other, but that's not some sort of memoryless equality thing. That's actually a change which can be undone, but which is not necessarily the same as the identity. And so when you look at the Poincare dual of a sort of picture like this, it's going to end up looking like something in 3D, and that 3D thing is going to look something like this. As we see, the A and B can be sort of rotated around each other, but we have to record how that works by using these kind of three cells. But you can also imagine that we could kind of unbraid these wires. As you know, if you've ever untangled your earphones, you can sort of undo the braiding, and that would be like inverting this sort of process. So, okay, we've started to uncover. So, okay, we've had a bit of a look at this table. There's much, much more that could be said. Again, I'd like to direct the interested viewer to John Baez's videos. They're better than these, quite frankly. He explains everything better, and he's got a wonderful paper called Categorification, which goes into more of the details to do with topology. But I just wanted to sort of echo one of the things he says, because it's a really magical connection between this stuff and topology. So I haven't spoken much in this course about topology, and I don't really want to get into all the definitions. So I'm just going to say something quickly, and you can look up the definitions yourself. But basically, there is a thing called a topological space. You could think of it maybe as a sort of generalization of a metric space, which itself is a generalization of like real space or whatever. So there is such a thing as a topological space, and topological spaces, they're sort of like generalizations of the spaces that we encounter. And topological spaces, there's these very sort of general ideas of spaces. And then the idea is that every topological space can be associated with a group, or a groupoid, or a n-groupoid, or even an infinity groupoid. So basically, there's this way of taking a topological space and then So the thing is that there's a really deep connection between these n categories and topology. So I just wanted to give a very kind of brief outline of this. So the important idea that I need to tell you about is this notion of a groupoid. Now, very, very roughly, a groupoid, an n groupoid is like an n category, but where everything's kind of invertible. And that's a little bit of an oversimplification. Here's a more So that's a little bit of an oversimplification. I want to be a little bit more precise. So let me tell you, I want to be a little bit more precise. So let me tell you about the idea of equivalences. So, okay. So, okay, an n groupoid is kind of like an n category, but where all the cells are equivalences. So what's an equivalence? Well, I'm showing a definition here. So the idea is that, let's say that you've got an n category, and then you have some cell, and you can ask yourself, well, is that cell an equivalence? Well, if it's an n cell, if it's like one of the highest dimensional things that you can have, then that's going to be an equivalence precisely when it has an inverse. That is something that you can compose it with, and you get the identity either way you compose these two things in opposite directions. So that's what it means to be an equivalence if you're an N cell. But what if you're lower dimensional? Well, then we'll say that something that's lower dimensional, like a J cell, F, is an equivalence when there's another cell going in the opposite direction, F bar, and F composed with F bar is like an ID, but up to equivalence. And similarly, F bar composed with F is like an ID up to equivalence. What do I mean? I mean that if we compose F with F bar, the result might not necessarily be an identity of X, but there is going to be a sort of higher dimensional cell which goes between ID and F bar F. And that high dimensional cell is itself an equivalence. And so when we're looking at something low dimensional and we ask if it's an equivalence, we'll be like, well, yeah, it is if there's a higher dimensional kind of equivalence between that thing and composed of identity and identity. So this definition kind of, if you want to ask if something low dimensional is an equivalence, then you have to exhibit this sort of slightly higher dimensional equivalence, and then you have to look at that. And you get pushed up and up in dimensions until you get to the n-dimensional things, and then you know if they are equivalences, because for them to be equivalences, they literally just have to have inverses. So this definition makes quite a bit of sense if you start thinking about like when proofs are equivalent of things, right? If you think about things like when proofs are equivalent. So you could say, for example, that are two arithmetic expressions equivalent? Well, maybe if you can use the laws of arithmetic to rearrange one into the other, you could say that means they're equivalent. But then you might have multiple ways of rearranging those expressions, and then you can ask if those ways are equivalent. But you probably want to bound the process at some upper point, like you say, only go up to 3 levels or something, and then you can stop. Or maybe there's other ideas where you can go all the way up to infinity, and this is sort of maybe a bit more like homotopy type theory kind of approach. Anyway, an n-groupoid, so this is what I wanted to get at. An n-groupoid is a n category where all the cells are equivalences. Okay, so it's kind of like you can always go backwards and forwards, and you have this high dimensional structure, but it's full of equivalences. And now we get to a really, really lovely connection, which is this connection with topology. So basically, if you have a topological space X, then you can speak of what's called the fundamental n-groupoid of X. And what that is it's a groupoid, it's an n-groupoid, and it's defined like this, okay? So the 0 cells are just going to be the points in the topological space. And then the 1 cells are going to be the paths between the points. And then the 2 cells are going to be what we could call the paths of paths, or homotopies between paths. So like a homotopy from P to Q, like this, that should be sort of endpoint preserving, basically corresponds to a sort of continuous family of paths from P to Q. So it's a way that we can kind of continuously deform P into Q and generate this family of paths. I'm not being especially rigorous here, but you can look up the details of this kind of stuff. And so we can go on. 3 cells would be like paths of paths of paths, or you can sort of visualize those as like surfaces. Like you can visualize those as sort of like volumes, like where you can deform one surface that represents a path of paths into another surface that represents a path of paths, and so on. So this is the idea of this fundamental n-groupoid of a topological space. So if you want to start thinking about things like get a sphere or a torus or something, and think about what kind of structure these n groupoids have. It's a really beautiful thing to study. But you know, in this kind of version of the theory, because we're only talking about n groupoids, we want to sort of cap this process at some point. So basically, when we get to the n cells, they're going to be these sorts of n-fold paths, paths of paths of paths, blah, 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 blah. But we only want to consider those sort of up to homotopy. So when we have two of these n-fold paths that there's a sort of n plus one homotopy between them, then we consider those equivalent. So we're only interested in the sort of equivalence classes of the n cells. So very similar to what I was just saying about equivalences. You sort of want to sealing off this process in some definite way. So for example, if you just wanted to consider the one groupoid of a topological space, then that would just be this sort of groupoid, which is basically just like a category where every arrow is an isomorphism, and the objects would be the points of the space, and the arrows would be the paths in the space. That's fine because the paths are invertible, but actually the arrows would be the sort of homotopy equivalence classes of paths. So like if you had like a sphere, for example, and you had two paths, those could be deformed into each other. So those would just be represented by the same arrow. But if you have like a torus, then, you know, if you have some paths from A to A couldn't be continuously deformed to other paths from A to A sometimes. Like if you have like a path around the sort of rubber ring of a tire or that kind of part of a torus. So this is really the idea of a fundamental group. And so the idea of a fundamental group of a space is that you can pick a point and then you can think about the different paths from that point to itself. So maybe this is a path P and this is another path Q. And sometimes you're going to have like a homotopy between those two different paths. Sometimes you're not. Like there's no homotopy between this P and this Q. And so you can separate, and so you can organize these different paths from X to X into homotopy classes. Homotopy classes like the class of paths that are equivalent, that can be sort of deformed into each other. And that gives you this notion of the sort of fundamental group of a space. Now, we can generalize this to get the idea of a fundamental groupoid of a space where, you know, we're not only interested in paths that go from a particular base point to itself, but we can consider paths between distinct points. But then we can go further and think about n groupoids. And a reason this is a lovely thing to do is this really magical kind of hypothesis here. So this is called the homotopy hypothesis. And what it says is that if you have an n groupoid G, then you can find a topological space X that has its fundamental n groupoid equivalent to G. Okay, so this is a really beautiful idea because it's basically saying that if you want to study n groupoids, you can do it all through topology. In other words, all of these n groupoids are appearing as sort of, they're appearing from spaces in some sense. So this is, we're sort of just scratching the surface of this really deep connection between these kind of non-strict n categories and topology. And I mean, hopefully you're already starting to see that. And I mean, hopefully you're already starting to see that things in this table are reflecting certain things on topology. So, for example, these braided monoidal categories have a lot to do with knot theory. but this connection goes very, very deep. And I think I'm going to leave it there. I'd like to, at some point, do a much deeper dive into this and talk about things like the loop spaces, infinity categories, which you can basically think, or infinity groupoids, which you can basically think of in terms of simplicial sets, or special kinds of simplicial sets called CAM complexes. And then there's all these connections with homotopy theory, and it's really just a very interesting subject. So if you want to know more about this, this document called Categorification, which is written by John Baez and James Doran, that's a really great resource.